Hello, everybody. Today is our 11th lessons from the series Computational Materials Design or for Newbies, where we consider different type of software where we can make models of molecules and crystals and other materials. So today our lesson would be somewhat different from the previous. On the previous lessons, we considered atoms as balls, just balls, connected to other atoms with some kind of like a sticks, which would represent the chemical bonds. Actually, today we'll take a look inside of the molecule to see how the electrons are distributed inside of their what's called molecular orbitals. And for this, we will use example of ethylene molecules, and we will be using the program which is called ArgusLab. This program is available free on Windows platform, and you can download it and also play it same way I will do, and also learn more what you can do with this program. There is pretty good tutorial in this program as well. So let me share the screen. So this is the screen of their ArgusLab program. So as you see, their screen is gray. In order for me to start doing something, I have to open the file or start a new one. So let me start a new one. So it shows some center and kind of line connected to whatever showed at the end, like carbon tetrahedral. So the number which is appearing here when I move the cursor is distance from these central points to the points where the cursor is. All right, so if I want to build the ethylene molecule, so I'm go and select the carbon from the menu, and I will need to get a trigonal planar carbon. Okay, so now if I go to the screen and click with the right mouse, I'll get one carbon atom. And for me to build the bond with the next one, I have to click here, which would select for me making the bond with the next atom which I create. So I'm going to click again and get the second atom. So same with the program of Avogadro, which we are used before in our previous letters. So we can add hydrogen, and since we selected trigonal carbon, it would know that the two atoms of hydrogen need to be added to each carbon. So I click on H hydrogen, and as you may see, there is two carbons atom. So for me to rotate molecules, I need to click here. So, and then you see, so this is ethylene molecule. So this would clean jig geometry, create it a little bit more realistic. I need to save it. I already have an ethylene file here. So overwrite, yes. Okay, so here's a somewhat clean molecule of ethylene. For me to get even more accurate geometry, I can use one of the quantum chemical methods, selecting, for example, A1, semi-empirical method, and then click on Run. So if you see here, there were some calculations which make geometry more close to what experimental values for bond lengths and angles will be. What we do next, so we will be looking up how their electrons are populated the molecular orbitals in ethylene molecule. So let's first count the electrons. So carbon, each carbon has 6 electrons, but 2 of them are on so-called inner shells, and they are not involved in the chemical bonding. So so 4 of them are. And each hydrogen has 1 electron. So in total, we'll have 4 and 4, and also 4 electrons from hydrogen, so 12 electrons. So electrons populate what is called molecular orbitals, up from their energy from the lowest energy to the higher energy by pairs. So if you have 12 electrons, so we'll have 6 electrons pairs occupied. So in order for us to show how the electrons are distributed on molecular orbitals, we go to single point calculations, select the methods. Again, let's do it the same, MAM1. And we go here in the surface properties and show that we want to select first 6 occupied. And you see this is what is called HOMO, highest occupied molecular orbital. So let's select it, and also lowest low LUMO, which is lowest unoccupied molecular orbital. So with this calculation, these molecular orbitals would be, their distributions would be calculated. So click on OK, click on OK here, and click on Run. So once I finish this, so we'll see that I calculated the electron distributions. So now I want to show how electrons are distributed in this molecular orbital. So I go to the surface and go to click on Make Surface. You see there's molecular orbitals show with sign plus. That means there is already information about these molecular orbitals. In order for me to make them visible, so I need to do the following operation. So I move them one by one here and create the surface. So it's for first one. This is for the second. This one would be our third. Great. Then next one would be number 4. I need to enumerate them, otherwise I would not get them correctly in a definition. So number 4, orbital number 5, create. Orbital number 6, great. And finally, orbital number 7, and create. Okay, so now in order for me to show how they look like, I need to click on select one of them. For example, we'll start from the first one, the lowest energy. Click on toggle display and click OK. So that's how the lowest molecular orbitals look like. So let's select their mesh type show. So you see the molecules, the electron distribution has the same sign, in this case negative, but it doesn't matter. It's important that it's the same sign. It means it's bonding in all areas. So at molecular orbital number 1 is surrounding the whole molecules. Let's go and look at the next one. So we need to delete the first one. Otherwise, they will be going one on the top of the other. So we select number 2, toggle display. Okay. All right, so that's how the second in energy molecular orbital look like. So we may see that it has different signs on 2 CH2 groups, and the bonding area is in the area of CH bonding, and no bonding in carbon-carbon bond. So this is orbital number 2. Let's go and take a look at the orbital number 3. So we go, toggle surface, click OK. So this third one would look quite similar in a sense that it also in the bonding in this CH bonding area, but in a different way. So in this case, it's the surface with separate bonding area is going through carbon-carbon bond and parallel, not perpendicular like a previous orbital. So this is our orbital number 3. All right, so okay, so let's go to see at how the orbital number 4 would look. So orbital number 4, toggle display, Okay, so the orbital numbers 4 looks interesting in a sense that it is has three separated bonding area. It's bonding in carbon-carbon, double bond, carbon bond area in the plane on the molecules, and also in the area of CH bonds. So this is orbital number 5. Let's take a look on the orbital number. This was number 4 orbital. So I'll go and delete one and take a look on the orbital number 5. All right. So the orbital number 5 look also quite interesting because it showed the bonding in CH and in CH bonds area. However, these bondings area are separated because for each bonds because it has changing signs, so plus, minus, plus, minus. So in fact, it looks like pi orbital in the plane. So if you can take a look, so that's how there are the last sigma orbitals. Sigma orbitals are those which are in the molecular plane. So this is their orbital number 5. And finally, we are going to take a look at their orbital number 6, which is the highest molecular orbital. And as we could expect, this is actually the pi orbital, so which is the highest molecular orbital. And obviously the reactivity of their ethylene and other pi bonding systems, they are predominantly related to these electrons which are highest in energy. So, and those are so-called pi orbitals. So as you may see, the bonding is above the molecular plane and below the plane. So there is no bonding in the plane. So this is orbital number 6, which is pi orbital. So as we may see, the lowest molecular orbital, you will see in a moment, is, oh, I did something wrong, just a second, surface, make surface, all right, number 7, toggle display. Okay, all right. So the highest, the lowest unoccupied molecular orbital is also pi bonding orbital, but it is antibonding. Antibonding in the CUC, the signs is different between two carbons atoms. The signs of electrons are distribution. So plus, plus, and minus, minus, plus. So this bond has no bonding character. So and this is lowest unoccupied molecular orbitals. So that's how electron distribution looks in such a simple molecule like ethylene. So that's that's actually conclude our lesson for today, and you can explore their ArgusLab both for for electron distribution in the different molecules and other electronic properties. So it's a pretty good program. Thank you so much.